go. All right. Get you guys, yep. All right. We are going to start class now. Sorry, little. I don't have the good talk though. Sorry. So, we were talking last class, and I was just incapable of thinking after a while, because of the whole bird thing, about carboxylic acid. So let's go back and just give us a review of what we did last class. Last class we were talking about Fischer esterification, which is the formation of esters from carboxylic acids. So we said, yep, we can do that whole chart thing, which I guess I'll always keep on the right board here because it's easy, like where I like to keep it, right? So we said that carboxylic acids can be converted in a reaction to esters. This is the one we were talking about last class. This can be a symmetric ester or an asymmetric ester, meaning these R groups can be the same or different, it doesn't matter, but they happen to be the same right now. And this is the reaction we were speaking of last class. We also said that we'd be able to convert this pretty easily to an acyl chloride here. That was a pretty easy reaction to do. But to get to an anhydride, that would be a little bit more difficult. We'll talk about that today. And to get to an amide, even more difficult. And we'll talk about that today. So really, as a preface to the next chapter, post-exam 2, right, which is on Friday, exam 2 is on Friday, we're going to be talking about these derivatives and interconverting between these derivatives. And what you can see is that carboxylic acids can move to form very easily acyl chlorides and esters, and not so easily anhydrides or amides. And at the very bottom of this chart are actually carboxylates, and carboxylates are even less reactive than the base neutral carboxylic acid. Okay? So this is the reaction we were speaking of last time. So let's just do a reaction like that. So we said that if you started with a carboxylic acid, you'd add an alcohol. Suppose we can add something like this. Note that you aren't ever going to be able to add an ether. Something like that is not something you can add. This goes back to sort of the language we knew, or the sort of concepts we reviewed with imines and enamines, okay? We said that with imines and enamines, we needed at least one hydrogen off of the nucleophile, the nucleophilic atom, in order for that bond to stick, right? Does everyone remember that? That a primary amine could add to a carbonyl carbon, a secondary amine could, but a tertiary could not, because there's no proton in order to make that bond stick. Same concept here. So ethers are a no, but alcohols are an okay. Both all primary, secondary, tertiary alcohols, because they all have an OH group, one hydrogen off of the oxygen. Okay? So in this case, we always know that we need to be adding an acid, H2SO4, which really gives me H plus and HSO4 minus, and probably even some SO4 2 minus. I actually think both of these dissociate readily. That's a Gen Chem concept. The first step here is going to be protonation of our carbonyl, as always. This step is reversible. Someone tell me why this step is reversible. This singular step here.
Acid-base chemistry.
The pKa's of the conjugate acids are similar, right? The pKa's of the conjugate acids are similar. Hence, the acid-base chemistry shows the equilibria that's associated with this reaction. Okay, we've then primed this carbonyl center for attack. Once we have protonated it, we have a resonance structure that clearly shows us then where any nucleophile that's sitting in the flask will enter at. Okay? The nucleophile that we have sitting in the flask is the alcohol. So as we've been talking about, this alcohol can go on and off and on and off until it itself is deprotonated, right? Our very next step here is that oxygen nucleophile coming on with its hydrogen and its R group. It has a positive charge. So this guy can come on, it can go off. It can come on, it can go off. This is an equilibria because the leaving group propensity is very high until deprotonation happens. Everyone understand what I mean by that? Would you be able to give me your own language back that suggests why this step is reversible? take the silence as a yes. So we move on, and we know that the next step then is going to be deprotonation of that nucleophile such that that bond can stick. Don't forget these arrows back. A lot of you are forgetting these arrows back. I don't like to do these guys. Yeah?
Does it matter what deprotonates that? Like, can the HSO4 minus deprotonate it?
So in this case, that HSO4 minus is sort of one of the really, that is something that exists in the flask. You should recognize that, right? When you go back to Gen Chem, right, and you talked about strong acids fully dissociate in water. They give H3O plus and a conjugate base. The conjugate base is there, right? It's HSO4 minus after the first deprotonation, SO4 2 minus after the second. That is a species that is allowed to exist. You know it has to. It has to exist. It's the only negatively charged species that can exist, okay? So that's just to put to bed some of the sort of runaround we had last week about whether or not that negative species can exist. The answer is yes, right? That is the conjugate base of H2SO4, and hence it has to exist if H2SO4 dissociates readily. We know it does because it's a strong acid. Now, the question of what can deprotonate here, in the first go-around, right? Honestly, the most likely thing to deprotonate is the alcohol. But this is true. Whatever this protonated species runs into in the flask that can deprotonate it will, which means if it runs into HSO4 minus, HSO4 minus will deprotonate that. Maybe not very efficiently, but it will. It'll, in essence, try to, right? The alcohol will, and eventually you're going to get water off here, okay? Eventually, water comes off in this mechanism. So water is also a safe thing to use to deprotonate. Anything that it will run into in the flask that can deprotonate it will deprotonate it, okay? So this is really about probability, and that's a whole kinetic theory concept, and that's a whole class in PChem, which we're not going to give here in a 50-minute lecture, okay? So it's a good question. So those are our three possibilities of acceptable things to deprotonate. HSO4 minus, another mole of alcohol, and water, because water eventually comes off, okay? Actually, there's probably a fourth thing, too. That carbonyl probably could, right, deprotonate it at times, but that geometry is very hard. That would be a hard geometry to get to. Okay, so once we see the deprotonation, we now have a tetrahedral intermediate that we need to consider what's going to happen with, right? So this tetrahedral intermediate, four things attached to what was once the carbonyl carbon. So we're still in acid, right? So now something else needs to get protonated. Whenever something gets protonated, I have, right, probability here. These three things can become protonated. If I protonate that alcohol, I'm moving backwards, right? So I've got to think of something new and novel that can get protonated, and that's one of those hydroxyls. So I'm cheating here with the H+, so we're going to let that go. And this is my next step. Should I make that 6 now? 3, 4, 5, yeah, I did. I'd love to do that. Now it's 4. You know what, we're just going to go back and just look at that carefully. There we go. That's the kind of stuff you like to catch me on. I'm trying to catch myself before you catch me. So now we have protonated water. The minute water is protonated, we know it can leave, right? Just like it can come on, it can go off. And this is a reversible process. Same concept of leaving group propensity here. So now I have this in the end. And all I have to do is, I've done the resonance structure, haven't I? So truthfully, this guy here, I'll get you in a second, that is the direct result, right? And then there's a resonance structure associated with that. Now we see we've gotten back to our carbonyl. We're good. We come out, and we can see that once we're out the other side, we have formed an ester from this reaction. Okay? And the ester here will be formed, in essence, when there's excess alcohol and acid in the flask. If I put any water into this flask, just throw in this molecule, right, this ester, usually solid, right, dissolve it in a whole bunch of water, say 50 milliliters of water, dump in some acid. Which way is this going? Everyone's pointed to the left. That's exactly right. We're going to go right back to the starting carboxylic acid and alcohol. You should be able to work this reaction forward and backwards. In the forward direction, we do call it Fischer esterification, as written here as the title to this. I have it plural, but Fischer esterification. In reverse, if I add lots of water and I'm pushing back to the formation of the alcohol and the carboxylic acid, that reaction is called hydrolysis. And you're going to see a lot of hydrolysis reactions in the next chapter. So it's language that I'm going to try and start using this week as we move forward. These reactions, when I plug them with lots of water and some acid, are called hydrolysis reactions. And they'll work back to the starting material. Now, one thing, if I had my head screwed on straight last time, I would have made a point to make you notice, is this is my starting material. And let's just look at my starting material compared to my end product here, which is this ester all the way down the line here, right? Just focusing on the carbon backbone. If I look at my starting material, my carboxylic acid, and my end product, my ester, I can see that I've moved into the realm that I'm no longer talking about addition chemistry, okay? Remember I said to you that there are two different acyl mechanisms. I spoke of this back some time. Remember we had the aldehyde and the ketone over here as sort of intermediary reactive partners between around the anhydride, but definitely before the ester and carboxylic acid. And we said those ketones and aldehydes do what we call nucleophilic acyl addition, right? The nucleophile attacks, and that's it. We get an OH, there's no leaving group to come off, right? There was not nary a leaving group. Wasn't there, didn't exist. Ketones and aldehydes do addition chemistry. The minute we hopped now into this next chapter and these next couple chapters, carboxylic acids and their derivatives, they actually do substitution chemistry, where you can see we're substituting the non-carbon entity of the carboxylic acid with a new and novel non-carbon entity. Now, we can see that we're running a lot of these reactions, or we're running specifically this reaction, maybe we should be just more specific to this one, in acidic conditions, because that allows us to create water which is a leaving group. The bottom, the difference here, why do these carboxylic acids and derivatives run substitution chemistry, is because they have a leaving group potential. They have leaving group potential, okay? These ketones and aldehydes never have leaving group potential, right? R or an H, R or an R. No leaving group potential there, but once I hit these derivatives, I have these leaving group potentials. Cl, acetates, I guess they'd be more specifically carboxylates, etc. Okay? So, carboxylic acids are running substitution chemistry, where you're swapping out the OH for something that's incoming. In this case, note, we're swapping it out for an OR group. Someone tell me why I had to go through all of this, which is a lot of chemistry and a lot of mechanistic work. Why couldn't I just say, take this guy and add in what I wanted? So why couldn't I add in something like this? Because that's going to gun, right? Don't you think it's going to gun right for the carbonyl site here?
It'll get protonated.
How many people think this is going to attack the carbonyl site? How many of you are never going to vote no matter what I say? Yeah, that's right. That's right. Okay, so I don't know why I'm questioning. If you have clickers, y'all are happy to vote. But no, raise your hand, no voting. Okay, this actually will run acid-base chemistry. The very, very first reaction you should always look at, whenever you are, now especially, where you are now, exam 2, exam 3, the final, the first thing you want to do is say, I have something and something over the arrow. Are those two things going to run acid-base chemistry? Very first question. Acid-base chemistry is the fastest type of chemistry that can occur before any mechanistic nucleophilic attack and electrophilic center, etc., etc. So always be on the lookout for this. This will not attack at the carbonyl center because this is going to run acid-base chemistry faster than anything, and what you're going to get out of it is something like this, and this reaction sits to the right. I have an acid on the left, that's the carboxylic acid. It's being T-protonated by this alkoxide. pKa of that carboxylic acid is 5. I come out to form the alcohol on the right, The pKa of the alcohol is 16. Okay? So this is an irreversible acid-base reaction. Okay? An irreversible acid-base reaction. A lot of people like to do this because, I tell you all the time, you either need a good nucleophile and an okay electrophile, or a good electrophile and an okay nucleophile. And everybody likes the good nucleophile, weak electrophile better. It seems to you all seems like the best way to go, right? And I understand that. It is certainly a faster reaction, but in this case, you'd be out of luck because you'd be running some acid-base chemistry. Okay? Are there questions about what I'm trying to do? Compare the acid conditions to the base conditions. Why we choose acid? Yes?
When you say acid-base chemistry, what exactly are you? You're just saying like protons moving, or?
I'm saying protons moving. Acid-base chemistry is a generic protons moving. That is the language we use when we say a proton is going to be moving around. Yes. Okay? All right. And we all agree that this is substitution and not addition. Alrighty then. Great. So this is the reaction from last class, and I remind you, make sure you can do the Fischer esterification and then the hydrolysis reaction. Okay. Next reaction is, yeah?
So it can only happen with another acid?
So this reaction, so, okay, let's just simplify down to maybe just reactions instead of looking at all this craziness. Maybe that'll help for you here. So if you were being asked on an exam, right, you're being questioned how to do this, right? The right answer is going to be this. And the wrong answer is going to be this. That was. Okay? So, you know, you always have those crazy reaction schematics. Crazy Dr. Dixon, right? So this answer on the left is the right answer, meaning correct. And this answer on the right is the wrong answer, meaning incorrect. We should do correct and incorrect. Yes, points. No, no points. You guys like that better, the points and no points. Okay, so do you understand what I mean? Yes?
Why do you need the H plus in the answer?
You need H plus because you won't be able to do any substitution chemistry off of carboxylic acid. This isn't a good leaving group, right? This OH, anytime you have an OH, right, if you have to make it a better leaving group. One way to do that is to run these reactions in acid, right? Because they make H2O through the course of the reaction, which then falls off. And that's where your substitution is allowed at that point. Yeah? Okay, so you'll note that I'm kind of always like swapping it out, and it gets maybe a lot very confusing, but I'm doing it purposefully, surprisingly. And that is because H plus really is a stand-in for some innocuous acid. H plus is fine. I'm okay with you writing that. However, there could be an exam question, say on the final, right, where we say, what is H plus a stand-in for? And there could be things you have to circle. It's never a stand-in for like HBr, right? Because HBr brings with it Br minus, which is a good nucleophile. HF, not a stand-in for HF, because HF isn't a strong enough acid. It's really only a stand-in for H2SO4 or H3PO4. In your mechanisms or in your reaction schematics, I'm fine for you to write H+, but you may be probed at one point in time if you know what the allowed H pluses are and what they're not. Yeah?
Didn't you add H plus to the first one?
To this guy?
Yeah.
Now, if I add H plus to this, then I'm not really adding a negatively charged nucleophile, right? So I wouldn't have really started with that. I'm not going to take a salt off the shelf, add a bunch of acid, and then do it, right? I'm just going to take neutral, cyclopentanol off the shelf and dump that in instead. But yeah, I mean, if you took this and you added excess H plus, you would get back to these reaction conditions, right? If you don't add excess, you're just going to get this neutral cyclopentanol back, okay? You got to stay away from the negatively charged sort of nucleophiles in general, especially when you're running with a carboxylic acid. Yeah?
What about the H plus, like in the mechanism? Is that all right? Or
Yes, this H plus is allowed too. A lot of you are doing that HSO4 minus H. That's totally fine. You can do that if you've gotten into the habit. You're not going to get lose points for that. But H plus is allowed. I know it's a lot of writing to do otherwise. So to limit your writing, H plus is fine. Okay, yeah.
I'm confused on how when you're considering acid-base chemistry, like how do you know it does go through acid-base chemistry or like, no, never mind, it's going to be substitution.
Okay, so if I saw this, I mean,
Yeah.
so you can write this out a different way, right? So if I see this, let me write up a bunch of things here. So let's just say this is, when you open a page to your test like this and you see this, you're like, oh my God, this all looks the same. What the heck is going on? I have no idea. So instead of looking at it in its totality, right, you got to go one by one. And one by one, this is my thought process as I work through this, okay? I see the first one, I'm not focusing on the rest of it because it will get me crazy. So I singularly focus. I'm right here at this top reaction. I say, okay, I have a carboxylic acid. I'm adding something that's a negatively charged nucleophile. Remember, this could also be written as something like this. So I have to remember to cross off the sodium and make that oxygen negative. Anytime you see those group 1s, cross them off, stick the negative back in, right? So then I'm going to say, the first thing I'm going to do is see if this is going to do acid-base chemistry. That's the very first thing I'm going to do. Now with this molecule it will, because there's an OH or an NH bond in here, OH or an NH functionality. If it was just a ketone or just something else, it's less likely. But because I have that OH or NH, it's going to do it. So this reaction is definitely acid-base reaction, okay? The outcome of this reaction is a deprotonated carboxylic acid and methanol, okay? So the first thing I think is, oh no, that oxygen's negative. Is it going to go deprotonate? So I'm going to check that. This is a good place to know very quickly how to manipulate your acid-base chemistry, right, to create a conjugate acid and conjugate base and judge that this reaction sits to the right, okay? This comes all the way from Gen Chem. Next thing I come to is I see, okay, here's my nucleophile, I have a carboxylic acid, I'm in acid, okay, I'm safe. I know there's going to be no, just straight acid-base chemistry. The acid is there to make this a better leaving group. So immediately I know that I'm going to be swapping that out. Okay, this is my base carboxylic acid, CH3, CH2, CH2, C double bond O, and then the O isopropyl. That isopropanol, because I'm in the presence of acid, is going to do Fischer esterification. Okay, I recognize this as Fischer esterification. Acid is safe. Okay, I come up here on the top right, and I consider this acid-base chemistry. If it's going to happen, because I have a negatively charged nucleophile. I got to be really careful, right? So this is one we haven't seen yet, so I'll be more careful. I'll write out the conjugate acid and conjugate base and write down the pKa's. So that's the first thing I'm going to do. I'm going to look at that acid-base chemistry and see if it's sitting to the right. So if I swap the proton onto here, I'm going to get something like this, O minus, and this is what I get, okay? The proton, the most likely, most acidic proton from the carboxylic acid is the OH. It's moved itself right onto the carboxylate here. In essence, this is the aeroformalism to show that, right? And this is what I get out. Well, I have a carboxylic acid on each side, right? So 5 to 5 generally. So this reaction's at an equilibrium. If I'm either sit to the right or I'm at an equilibrium, I'm going to let it go. That's all it's going to do, really, is the acid-base chemistry, okay, at this point in time. All right, and the last one here is NH3 tricky one, because it doesn't have to be NH2 minus here. Remember, NH3 is a moderate nucleophile. It's a moderate nucleophile, so it's got some basic properties. Its conjugate acid is NH4 plus, pKa 9.4. So I've got to be careful of this guy. This guy is really, really tricky. So I'm going to see what happens. Let me just analyze that acid-base chemistry and see if it does indeed sit to the right. So I look at this, and I have a conjugate acid on the left, or an acid on the left, the carboxylic acid, pKa is 5, right? 5. I have an acid on the right, NH4 plus, the pKa is 9.5. This reaction really is sitting to the right. Okay? I mean, every reaction has some reversibility, but we're definitely not a true equilibrium. We only have some sit back to the left, right? And hence, this reaction is an acid-base reaction as well. Okay? So the very first thing I'm at is to take what I have and see if it's going to deprotonate that carboxylic acid. The only one I didn't do was this one, because there's never going to be that when H3PO4 is present. Okay? Or H2SO4 or H+, whenever acid, strong acid is present. Okay? Does everyone understand what I'm doing here? Yes?
Is the Fischer esterification reversible?
Yes, the Fischer esterification is reversible. I didn't show that with this because we were just talking about reaction outcomes. Yes, it is. Absolutely. Thank you. Uh-huh.
Acid-base chemistry, and if they're really different, and it's acid-base chemistry, when does it not do acid-base chemistry? When the pKa's are what?
So,
Okay, that's a question that was actually on your assessment as well.
Okay.
Just, you know, go back and almost everybody got it wrong. Which, that's okay. It's definitely not an easy concept. What I would think about with that concept is just to go back and look at the two different conjugate acids I can create in the presence of H+. Okay? So when I look at R, C double bond O, OH, there are two oxygens that can become protonated in the presence of acid, right? So I can call this, say, oxygen A, and this oxygen B, okay? So I'll draw the conjugate acid when oxygen A is protonated. That's this guy here. And I can draw the conjugate acid when oxygen B is protonated, and that gives me this conjugate acid here. Okay, so all I did is stick that hydrogen onto each one of those oxygens, using an electron pair, checking formal charge, gives me a plus on the carbonyl oxygen or a plus on the oxygen that was once the OH. Okay, now OH2. And now I look at these two in a comparative way, because I want to judge which one of these is more likely to pick up that hydrogen. I want to look at the outcomes. Which one of these is more stable? And the answer is the top one, because the top one has a resonance structure, right? This has a resonance structure, so there's equal sharing of that positive charge by two oxygens, whereas the bottom does not have a resonance structure. So this is proof in the pudding why the carbonyl oxygen is always the first one to be protonated, and this will also be true when we look at amides, esters, everything, okay? It's always the carbonyl oxygen that gets protonated first. And that's why that's the first step in Fischer esterification. Okay, yeah?
For these, are we just looking to see if they will undergo acid-base chemistry? Is that
Yes,
what we're
I was saying, are they going to undergo acid-base chemistry? We were a yes on acid-base chemistry. We're a yes on acid-base chemistry. We're a yes on acid-base chemistry. We're a no here. So I drew the outcome of what, if it's not going to do acid-base chemistry, I then say, what is the substitution that's going to happen? And the substitution that's going to happen is this OR, right, in place of the OH. This is the Fischer esterification reaction. Yeah.
just to confirm, it's going to do acid-base chemistry if it sits to the right or if it's at equilibrium.
If it's at equilibrium or if it sits to the right, I have to guarantee that that acid-base chemistry is an important step in the reaction mechanism. Yes. Okay? All right. Now, sorry, yes.
Starting materials kinds of
Yeah.
No, we don't use them as bases. We can talk about that more after. Okay, so I've just proven to you, because you guys were pushing me with this acid-base stuff, I'm just telling you that you've proven here why I don't have an arrow, okay, between this RC double bond OH, right? And truthfully, you definitely proved this one to an amide, okay? This you might think I'm going to be able to work in some acid conditions and get that to happen. The truth is that can only create symmetric anhydrides. I want you to think about this reaction here. You tried, or we tried, right? We tried to use a carboxylate to get there. We're a no on that. So then the question is, could you add something, could you do something like this? Okay? I have R prime, a different R group, C double bond O, OH, and acid. Could you do a reaction like this and swap out the OR, or the OH for the OR prime, or something like that? Can you do that? I want you to think about that before next class. We'll start with clickers on this guy here. But you've absolutely proved why we're not going to go this way, okay? So I'm not going to talk about that the remainder of today, but you want to put in your notes that you know the answer to why we aren't going to form this readily. We're going to see that this is not going to form readily. Why we're not going to form this readily, okay? There's a couple other reactions we need to get through with carboxylic acids, namely the top one, how to get through to the acyl chloride. So to get through to the acyl chloride, we must be swapping out that OH for a Cl, right? If I think about that reaction, I'm going from an OH through the use of thionyl chloride here, I'm going to a Cl. So I'm moving from a carboxylic acid to an acyl chloride. Now this has nothing to do with acidification. There's no acid present here at any point. But it is still working around the same principle that this OH is not a good leaving group. Okay? But in this case, the reaction is primed with thionyl chloride. We've seen thionyl chloride create a chlorosulfite, which is a better leaving group than the original OH. Okay? You should have seen that and heard that language from OChem 1. We're going to look at that mechanism right now. So, your reaction here is between a carboxylic acid and thionyl chloride. Thionyl chloride looks like this. Okay? Truthfully, the reaction starts from this oxygen. Going back to your question in the back, I forgot your name. What's your name? Yeah. Thomas. Okay. Thomas asked this great question about how do we know this oxygen is the one to be protonated. This oxygen is the most nucleophilic. What we actually see is this arrow to get from the get-go. Does everyone see what I've done? Okay, it's coming from the carbonyl oxygen. Coming up to that sulfur, this is the formation of a tetrahedral intermediate centered on the sulfur. Anytime I take an sp2 CO bond, double bond or SO double bond, right, and I attack a nucleophile, electrons get pushed up onto the oxygen and I create a tetrahedral intermediate. This tetrahedral intermediate will be centered now on the sulfur and not on the carbonyl carbon. So we have something like this now. Okay, tetrahedral intermediate, right? 4 things attached, tetrahedral intermediate on the sulfur. Okay, this oxygen is positive. Okay, there is a resonance structure here that exists. So this is what I get. Just like a CO double bond wants to try and collapse, right, and reform, which is what we were looking at with Fischer esterification, right, the collapse, it wants to reform. It can reform here at the sulfur because this negatively charged oxygen can start saying, okay, I'm negative out here, I want to make my double bond back. This is commonplace in substitution chemistry of what we're seeing. This is all substitution chemistry. This reforms, it's got to let go of a leaving group, right? It's got to let go of a leaving group. So the leaving group it's going to let go of is a Cl. That's the better leaving group. Okay? So you can see that from this guy too. It doesn't matter which one I draw it on. The Cl is what's let go. And what we form through this reaction here does have some reversibility associated with it. If you look up the leaving group propensities, CL just edges it out. It's not a wham bam, right? It's not a, yep, I'm the best leaving group there is, right? It's a moderate at best sort of win over the other leaving group possibility. So there is some equilibria associated with this. And in the end, I get something like this out. Okay, this here is my chlorosulfite, right? Chlorosulfite. My chlorosulfite is now a good leaving group. Probably just as good as the Cl, but it's a pretty good leaving group. You'll see there's a reason for the irreversibility of this reaction mechanism in just a minute. This is the intermediate that I wind up with. Okay? In the end, yeah.
Why doesn't it take the proton off of that oxygen in that resonance?
The Cl minus?
The O minus.
The O minus? Okay, it appears that this geometry is set up properly for that, especially the way that we have it drawn. It is not actually. So all of those like online sources that you guys like to find that do those intramolecular like proton captures, yeah, they're all bad. They're all doing an illegal thing. That just doesn't happen. You think about the geometry necessary, you find that the geometry can't be set up for that to be a probability. So that is why. I see that you want to do that though. I mean, I get that. Okay, so we're out here, okay? We're out here, and now I have the ability to break down this intermediate and give back now a very interesting outcome, okay? What actually happens is this bond comes to capture this Cl. That Cl's going, right? It's going with that H. I'm forming HCl. This is in essence saying, hydrogen's taking its one electron, right? It's coming, or it's two electrons, I guess, it's hydride, and coming to take a bond to Cl. So Cl's off and running, okay? Off and running. So what happens here is, I get back now, truthfully, it might be easier, so then I don't have to do so much explaining, and maybe easier than the intermediate I was about to create. So we get something like this. We're going to come and steal this. This is going to come back to form SO2, and what we get in the end then is the reformation of the carbonyl here, okay, and the Cl attached. In the end, I can see that we don't have a tetrahedral intermediate. You guys are all looking at me, and I'm looking at me. I'm like, where did that other Cl go? Scrap that. My bad. This is still a chlorosulfite. I can see what I did. My bad. Thinking too far ahead. We didn't attack the Cl minus. Silly us. Silly me. Here we go. Now we're good. Now I'm happy. Like, what the heck?
Wait.
Hold on. I'm backtracking. Right. I have now a good electrophile. What I didn't do is my last step here, which is attack of the Cl minus at my good electrophilic center. This is the step that I was missing. I thought I already did it. Obviously didn't when I was looking at my intermediate. Okay? So this Cl minus comes and attacks this electrophilic center. What I get out of it now is a new tetrahedral intermediate. This tetrahedral intermediate, though, is centered at the carbon, what was once the carbonyl carbon, and not the sulfur. And we can see that we're at the substitution site now. We're at the point where I can do my swap out, right? This here is my waiting in the wings carbonyl. This here is what I'm trying to substitute for the chlorosulfite, right? So I'm trying to get this as a substitution in for this leaving group, okay? Now, they have equal propensity as a leaving group if you measure just by pKa alone. So the bottom line is it comes down to the fact that thionyl chloride comes out as a gas, okay? So watch what happens here, okay? This hydrogen comes stealing that Cl. These electrons get kicked back. That's now SO2, okay? That's now SO2. And in the end, you get now your substitution, and thionyl chloride, sulfur dioxide, comes screaming out of this reaction, okay? and HCl. HCl came out as well. Okay? So, in essence, what happens here is you get reformation of the carbonyl, because this had to leave a bond as well. I have sulfur dioxide coming out, and I have the ability now to form the acyl chloride. Yes?
Do you have electrons bound from the H to Cl or
That's a good question. It actually must be the other way. I do. You're good. All right, my bad. Minus one, Dr. Dixon. Okay, so in the end, the chlorosulfites always do this. You saw this with alcohols as well. Okay? They always do this. They create the sulfur dioxide coming out, never coming back. So if we come back around, I'll give you just a second, Audrey, so I can finish my reversibilities. We made a big stink about the reversibility here. I was saying here, and I didn't come back and put any formalism on the board, but I was saying here that this step is also reversible. I said if you compare just the pKa's, Cl can come off, or this chlorosulfite can come off, right? The chlorosulfite comes off, I'm moving this way, okay? But if the Cl comes off, possibility, I'm moving backwards. So I'm reversible, reversible, reversible until I get here. This is where my irreversibility comes out. This last step is irreversible in the formation of the acyl chloride because of the fact that sulfur dioxide comes off and out of the system and bubbles away. Audrey?
I'm just confused about the arrow on the chlorine here going to the oxygen in that step, and it's also in that other step.
Okay, well the bottom line is just negating arrows, just so we can make sure you can follow what's going on. This comes off, this is HCl, right? This comes off, and this is sulfur dioxide, and we're left behind with our framework for the acyl chloride, and that's really, this is the main frame, right? This piece is just explaining an irreversible last step. Yes?
So does the bond to the oxygen go to the SO2?
Yes, there is a reformation here that starts the whole thing. Okay, there's a reformation of the carbonyl that starts the whole thing.
Does that make a partial positive then? Or would that
No,
not happen?
it doesn't, because you have a leaving group coming off. Yeah, I mean in the transition state there's a partial positive, yes. Okay, so this is the next and almost last reaction before we get to the end of the line. So the last one that I want to talk about today, and I'm hoping I have some time left, 5 minutes, good, is the reaction of lithium aluminum hydride with carboxylic acid. Okay? Now, this is a place where really what we can do is count equivalents, and it's probably the best thing to do.
Yeah. Yeah, it should be in this one.
Then this will give
But I think I got it right.
I'm going to get behind the scenes on that last one. Good follow.
I'll send you.
Use lithium aluminum hydride with an aldehyde. We're only ever using one equivalent of lithium aluminum hydride, right? Only one hydride is being used, and it's being used as a nucleophile. We saw this reaction, right? We saw the reaction such that we had this molecule took its hydride as a bond, passing it to the carbonyl center, and forming an intermediate, tetrahedral intermediate that stalls out. These tetrahedral intermediates do not collapse back. So in this case, this tetrahedral intermediate was the end of the line. There was some acid-base chemistry or nucleophilic attack at this new aluminum center that's created, right? That could make some sort of salt up here, but negating that, that's pretty much all that can happen. We formed an alcohol, right? We're using one equivalent. When we turn the tides, and specifically, you want to put a little note in your notes here. What I'm about to talk about with the carboxylic acid is very similar to what's going to happen with the amide. That'll be very important to you when you're reviewing for the final exam. There's different chemistry that happens here because if you stick lithium aluminum hydride in with this molecule, the first thing that you're going to see is acid-base chemistry. Lithium aluminum hydride is a base. You're putting it in with a carboxylic acid. The very first thing that's going to happen when lithium aluminum hydride is presented in the same flask as a carboxylic acid is formation of the carboxylate, okay? And that's a reversible reaction, okay? That's a reversible reaction. So this is it. One equivalent is used for this very reason here, okay? Now, depending on where you look, depends on where we go with the mechanism. I've not pulled the primary literature on this. I have not yet done it. Every time I teach this unit, I'm always thinking I need to go back to the primary literature. I haven't done that yet. But there's two different modes of thinking here. Generally, what I show is the attack at this type of intermediate, the aluminum trihydride, which is now a good electrophile, right? ALH3 was formed right here, right? This is being let off right here. Here is ALH3, okay? It's a great electrophile, group 3 atom, meeting an octet, okay? The oxygen, great nucleophile because it's negatively charged, right? So I have nucleophilic attack at a really good electrophilic center. And what I get out of this then